In this video, we're going to explore the Bohr model of the atom. So we're going to take some time to review electromagnetic spectrum and the electromagnetic radiation. So electromagnetic radiation is light energy, and light travels at 3.0 times 10 to the power of 8 meters per second. So basically light travels really fast. And it travels in waves in bundles of energy called photons. And if you look here, this is a diagram of the electromagnetic spectrum. And you can see there's only one part that we see with our eyes, and that's the visible spectrum. If you go this way, the distance between the waves, the wavelength, gets bigger and bigger, so quite large. And if you go this way, the frequency, so how often the waves repeat themselves, increases. And the energy increases in this direction. So the shorter the wavelength, the greater the frequency and the higher the energy. So if you look over on to the left of the visible spectrum, you have UV rays, which we know are dangerous. They can cause skin cancer and mutations in our DNA. X-rays, we also know that they can be dangerous. We have to limit our exposure to them. And then gamma rays, which are really high energy waves and are very dangerous. Now, if you go to the right of the visible spectrum, we have infrared, which is low energy, microwaves, and radio waves. So these are lower energy waves and less dangerous. So as I mentioned before, wavelength is the distance between two peaks in a wave, and the shorter the wavelength, the more energy the wave has. So this wave at the top, the wavelength is very short, so there's not much distance between each wave, so it has way more energy than this wave, which has a much longer wavelength and less energy. Frequency is measured in Hertz, and it's the number of wave cycles per second. So high energy waves would have higher frequencies. So this one's repeating much faster over time than this one. So the top one would have more energy and higher frequency. So a little recap from grade 10 science. If you remember, we learned that what we see in terms of color is actually the reflection of the wavelengths of light that an object can't absorb. So if you remember, light travels in straight lines. White light is made of a mixture of all colors of light, and you probably did an experiment where you would shine light through a prism and it would scatter the light into the visible spectrum. And the color of an object depends on the light that it reflects. So if we imagine that all white light was hitting a green leaf, it would absorb all the light rays except for green, and green would bounce off and back into our eye, and we would see green. Line spectrums have distinct colored lines, so different types of matter emit different line spectra. And we can identify a sample of matter by the line spectra of light that's being reflected back to us. So it's like a human's fingerprint. And we will be doing a lab activity where we'll look at the line spectra of different elements and other substances. Now, an emission spectrum shows what light is being reflected, and an absorption spectrum shows what light is being absorbed. So if you look at this one, this is a continuous spectrum, so we can see all the colors of light. An emission line spectrum is the wavelengths of light that are being reflected. And then an absorption line spectrum, you can see wherever the colored line was above, there's a black line. So it's showing all the light that's getting absorbed and omits the light that is being reflected. So if we recap a little bit of what Bohr understood, so from grade 9 and 10, Bohr believed that electrons orbited the nucleus kind of like planets around the sun. So you probably learned how to draw a Bohr model where you would draw the nucleus and show how many protons and neutrons were in the nucleus, and then would draw orbits around and then put 2 electrons in the first orbit and then 8 in the next, and so on until you've distributed all your electrons. So Bohr said that the energy of an electron is quantized, which is a big word for just saying that it has different energies at different orbits. So different energies at these different orbits. So if an electron absorbs some light energy, it would get excited and jump up to a higher energy level. And then for the electron to go back to its correct orbit, it would release that energy in the form of light and go from its excited state back down to the ground state. So if you look here, this one, it's absorbing some energy, and the electron got excited and jumped from this orbital up to this orbital. And then it wants to get back to its correct orbit, so it drops back down and then releases that energy in the form of light, and we see that light. And so we call that an emission spectrum.